Okay, so you can, so welcome back. So you can prove related results. And here is something more delicate. So let me state it as a proposition. So again, suppose mu is log concave. Then for every bounded f, PTF is Lipschitz. And Lipschitz constant is like 1 over square root t times the L infinity norm of f. Okay, so proof. So how does it work? So again, let's use some coupling argument. So I will use PTF of x minus PTF of y. So it's smaller than expectation f at xtx minus f at xty. Except that the difference here is that I want to upper bound this only by the L infinity norm of f, not the Lipschitz norm. So there's no much I can do. The only thing I can do is say this will be 0 if xtx equal xty, and otherwise this is so this will be smaller, let's say 2 the L infinity norm of f times the probability that xtx is different from xty. So I need to find a coupling for which this is small. Okay, so now the coupling that I choose before, where I choose the same Brownian motion, this is awful here. Because if you take the same Brownian motion, you see from the equation that I erased that actually the two processes never meet. So this is always, this probability here is always 1. So not very good. So I will choose the Brownian increment for xty to be the reflection of that of xtx with respect to xtx minus xty perp. Okay, so let me draw a picture. So suppose this is xtx. Then I will do some jumps, so some Brownian jump. Okay, so this will be like the dwt at xtx. And here this is xty. And I will choose the Brownian motion here to be the reflection with respect to this hyperplane. So I choose, I draw a picture where the reflection is not helping me, like it's going further apart. But in some cases, it will help me because I will, okay. So if you do it a bit more formally, but not too formally either, you see, so dxty. So formally, it's identity minus 2 vt tensor vt dwt minus grad v at xt y dt. Maybe I forgot square root 2 here, where vt is so this is supposed to be this orthogonal map here, this orthogonal reflection. So vt is probably xt minus y minus xtx minus xty normalized. Okay, so actually, I only do that up until the first time they've met. Okay. So for t less than tau, where tau is the infimum such that the two processes collide. And let me write it here. So after time tau, we just set xty equals xty. Okay, I will not go into the details so as to show you why this is well defined. Okay, but I mean this is a standard tool in diffusion. It's called mirror coupling. Mirror coupling. And you see the reason mirrors. It's like the Brownian motion, like this one is what you see from this one into a mirror. Okay. Okay. It turns out that now if you then if you look at the, so I will skip some of the computation, but if you apply Ito to the Euclidean norm applied to xtx minus xty, you have some term that cancel out. So basically you have no Ito term. The reason is that if you do xtx minus xty, the Brownian jump is only in the direction okay, x, xy. You will only have a Brownian jump into this line, okay, on this direction. And on this direction, the Hessian matrix of the Euclidean norm, it vanishes, because the Hessian of the Euclidean norm is you have to project down, okay? So you have no Iter term. And you see that this is square root 2. So you will have maybe Vt dWt. Okay, maybe there is a 2 here because that's the way it is. And you have like the term that comes from the gradient, okay? And the gradient will give you from grad v, so we'll give you minus Vt grad v at xtx minus grad v at xty Vt. And again, remember that this guy xtx minus xty divided by norm. So again, this guy here with the minus, okay, with the minus. This is negative if B is convex. And Vt as norm 1. Almost surely. So integral Vt dWt. Yeah, too many t's, but is a standard one-dimensional Brownian motion, which I call Bt. Okay, so up until time tau, so until the first time they meet, we have xtx minus xty. This is upper bounded by what you have at time 0. plus some constants, so it's maybe 2 square root 2 times some 1D Brownian motion. All right? And this Brownian motion is helping you, okay? This is, okay, in the picture I told you, like sometimes it's not helping, sometimes it's going to the right, but sometimes you will go to the left, so. Sometimes it will help me. And so the probability that xtx is different from xty, so which is the probability that the two processes have not met. Tau is bigger than t. Okay, so this is the probability that this Brownian motion here has not hit the value minus this value. Okay? For every s less than t, bs is larger than minus x minus y divided by 2 square root 2. Okay, yeah, I'm confused with the signs. No, it's fine. Okay, maybe, okay, I will get confused. So maybe I'll just change this way. This is the same, minus b has the same law as b. Okay, so the probability that my two processes have not met is smaller than the probability that a 1D Brownian motion doesn't exceed a given value. Okay? But this we know what it is by something called the reflection principle. No, okay, I will. So it's called a reflection principle. Okay, if you start a Brownian motion from 0 and you fix some value, the probability that it has exceeded the a for some time less than t is twice the probability that it's larger than a at time t. Yeah, I don't know if anyone is following here, but okay, I will write it, then it will be easier. Probability that there exists s less than t, bs larger than a, is twice the probability that bt is larger than a. The reason for that is that you condition on the first time you hit a, and then condition on the fact that you've hit an a, you have half and half chance to be to the right or to the left of a. And these two here. Okay, so this guy here, yeah, maybe I'm confused. So it's 1 minus this. So it's 1 minus 2 probability that bt is bigger than x minus y over 2 square root 2. Okay, so it's twice the probability that BT is smaller than, no, there is no 2 here. BT is smaller than x minus y by 2 square root 2. So it's the probability that some standard Gaussian is small. So let me call, I don't know, phi of where phi is like, would be the distribution function of this guy. Okay. Okay, so it's I don't know, integral from 0 to a e minus x squared over 2 dx over square root 2 pi, and maybe there is a 2. And then you're done, okay? So if I start from the very beginning, I get that the Lipschitz constants of PTF is smaller than où est-ce qu'on a été là? To infinity supremum over x and y of phi of x minus y divided by 2 square root 2t over x minus y. But this phi function here, the supremum of phi of a divided by a is something is confusing for me. Hang on. Yeah, in any case, you get okay, you get 1 over 2 square root 2t sup over a psi of a divided by a, and this is a constant, like maybe 1 over I think it is square root 2 over pi. In any case, you get some constant divided by square root t. Okay? Some constant divided by square root t. Somehow I promised the constants would be less than 1, but I'm not sure anymore. But it doesn't matter. For me, this constant doesn't matter. Yeah, it looked like pretty smaller than 1, but okay. Here is a corollary. Okay, by the way, I think this is due to this lemma here is due to Varopoulos, but not a proof like that, a different proof, as far as I know. Here is a corollary which is due to Michel Ledoux, and we state that follows. When mu is log concave, so again, if mu is log concave, f minus PTF in L1 of mu is less than 2 square root 2 no, hang on. Is it the? Yeah, it's grad f L1. Yeah. Yeah, which is f. It's the same. No, grad f L1. Yeah, sorry. And also, for any set A, if you look at mu of A, 1 plus mu of A, which is the variance of the indicator of A, then you can control it by the variance of PT times the indicator of A. And here you have square root maybe 2t, I don't remember the constant exactly, mu plus rei. And the proof is, so it follows from this last result, because it's if you want, this statement is somewhat dual to the other statement. Because so you look at f minus PTF and you look at this against some function g in L2 of mu. Okay, but then because of this PT is self-adjoint, you can write it as f g minus PTG. Okay, and this, the derivative of this, so this is integral from 0 to t. Okay, so recall dt pt g is L pt g. So this is integral from 0 to t of f L psg ds. Then you integrate by part. This is minus, okay, maybe. Okay, I don't care about the minus, but okay, let's try to be correct. Maybe there was a minus here, so it's plus. Anyway, I will use Cauchy-Schwarz, so it's okay to make mistakes here. Grad PSG ds. No, I don't use Cauchy-Schwarz, but I use something like Holder. So this is less or equal incident from 0 to t. So this I will upper bound by the L1 norm of grad f, and here by the L infinity norm of grad PSG. So this is the Lipschitz ds. But this is basically 1 over square root s. So I will get 2 square root 2. Okay, this is 1. This is g. So hence the claim, okay? PTF f minus PTF g is less than this times the L infinity norm, so it's indeed saying that the L1 norm of this guy is. And for the second statement, which is behind here, so you can, yeah, if you have X-rays or something, you can read it. So if you apply to some Lipschitz approximation of indicator of A, you will get 1A minus PT1A L1 is less than 2 square root 2. So basically the gradient, the L1 norm of the gradient of the Lipschitz approximation will converge to the measure of the perimeter. And this, you can like massage this, and you will see that it's the same as twice. Yeah, you have to use the fact that PT is self-adjoint again. But you'll see, so I'll spare the details, but this is the same as twice variance of I minus var of P, maybe T over 2, 1A. Hence the result. Again?
Can you please repeat how you conclude the first part of the statement from what you did? Like, how do you get this L1?
Okay, I see. You see, I obtain integral f minus PTF times g d mu is less than 2 square root 2 grad f L1 times the L infinity norm of G. So this is a duality, like saying this amounts to saying like, okay, if you apply this to G, that is the sign of this function, then you get the L1 norm. Okay. This is for every G. Maybe this is what okay, and so hopefully I will have time to motivate all this and prove to you Boozer. Okay, actually I will do more than Boozer. So I will give you a theorem of Emmanuel Millman. So before I state the theorem, I will state some other theorem on which it is based. So if mu is log concave, then the isoperimetric profile of mu is concave. So what is the isoperimetric profile of mu? It's I mu of t is the infimum of mu plus of A over all A such that mu of A equals t. Okay, so this theorem, so I will use this as a black box because this uses really deep result from geometric measure theory. So the good reference for this, if you read French, is Vincent Bayle, PhD, says this. Or you can read in the paper by Emmanuel Millman. You have like an appendix with all the history about this problem and all the relevant references. Okay, this is very convenient, this concavity of isoperimetric profile, because since I of mu is positive, concavity implies that I mu of t is larger than twice I mu of 1/2 t 1 minus t. Okay? I mean, if you have I of mu 0, 1. You have a bound at 1/2. If you know that the profile is larger than this, then it must be larger than this. In other words, the Chigger constant of mu is less than 1/2 times the isoperimetric profile at point 1/2, which means that in order to lower bound the perimeter of a set of any measure, you only need to consider sets of measure 1/2. Okay? And if you combine this with all this nonsense above here, you arrive at the following corollary. If mu is log concave, there exists a function f, which is one Lipschitz, and such that the Poincaré constant of mu is roughly the same as the variance of f. It's also pretty much the same as the Chigger constant square of f. So in particular, the Poincaré constant and the Chigger constant are about the same. And it's also, for what it worth, it's also actually the L infinity norm of f squared, pretty much. Yeah, I keep making this same mistake and writing the. Okay. Maybe I'll rewrite the statement. Okay. Okay, I will just sketch the proof. So you start with A, which is near extremal for Chigger with the measure of A, which is 1/2. Then because of the concavity of the, so you would have that mu plus of A is roughly speaking 1/psi of mu. And then you regularize this guy. So you consider a PT indicator of A with T, which is of the order of 1/psi of mu squared, and apply the two propositions. And maybe let me just skip what is my my function f. It will be maybe I will just give you and I'll let you come up with the detailed proof. No, sorry. Sorry, the T should be, yeah, sorry, I got it wrong. T should be of the order of psi mu square, and F should be more or less psi of mu times PT1A. Okay, if you choose the constant appropriately and you use the different proposition that I gave, you will see that this pops out. So let me just finish with some consequences of this result. Okay, so consequences. So we get the Boozer result. Psi mu square is about P of mu. But actually we get much more. Because you see, I have a one Lipschitz function which whose variance is about as large as the Poincaré constant. So this means that Cp of mu, it's about the same as the figure constant, but it's about the same as the supremum variance f for which with f one Lipschitz. This is stunning in a sense. I mean, okay, Cp of mu is the base constant in variance f less than Cp of mu integral grad f squared d mu. What I'm saying here is that actually you can replace this by the L infinitorm of the gradient. You still get the same inequality up to a constant. So this is very helpful. This means when you want to prove Poincaré, you can upper bound this by the L infinity norm, and you still recover Poincaré. So this is very, very efficient, and this deep result is due to Emmanuel Millman. The proof sketch that I gave is not really the same as what the Emmanuel Millman does. It's more inspired by Ledoux's proof of the Boozer inequality. Maybe I should make an additional comment that actually I have a bit more in my corollary, which is erased, which is here. I have a bit more information. I also know that the infinity norm of f is also the same as the variance. So I can, if I want, I can also assume f infinity norm, which is about the variance. No, I can add this hypothesis on top. So it's enough to bound the variance of a Lipschitz function whose L infinity norm is the same as the variance, roughly speaking. One last thing I want to say is that, as you can see from this, is that often for log concave measure, you can somehow reverse the hierarchy between functional inequalities. And here I only show you the example of Poincaré and Shiger and of this weak notion of Poincaré, but this is true actually for other type of inequalities. So this is something I wanted to tell, but I don't have time anymore. So let me just mention it here. I'll just give you the statement. And I will drop some words that maybe many of you won't know, but so in general, so similar, there's a similar result for log Sobolev. So log Sobolev is some inequality which is stronger than Talagran's transport inequality. Which is itself stronger than, okay, maybe I should write it here. Gaussian concentration, something that I didn't have time to mention. And all these implications are quantitative, namely the base constant in the Gaussian concentration is smaller than the base constant in Talagrand, which is smaller than the base constant in log Sobolev. All this is reversed for log concave. So for log concave, they are all equivalent and with a matching constant. I mean that the log Sobolev constant of mu would be pretty much the same as the Talagrand constant of mu, which is the same as the Gaussian concentration constant of mu. So this is somewhat parallel to the result for Chigger and Poincaré. And this is also due to Emmanuel Millman. And for this result, you have actually a bunch of proof in the literature, but you can prove it using similar ideas as what I explained to you. Okay, I guess that's all for today. Je vais dépasser là ou pas?